the geology and landscape of Mexico's Central Valley. This video is based upon a presentation given to the High Wycombe and District U3A Geology Group by Keith Spencer, October 2025. The script is by Keith Spencer. Video production by Phil Platt. Narrated using Play HD AI voice. This talk has an unusual background. My wife and I have been to South and Central America a number of times, but we have never been to Mexico. So when the National Gallery in London had an exhibition of Mexican paintings, we decided to go and have a look. The paintings were by the late 19th century painter José María Tranquilino Francisco de Jesus Velasco Gómez Obregón, who, thankfully, is better known simply as José María Velasco. He turned out to be a really interesting character. He was not a celebrated artist like Monet or Picasso, but he has been described as borderline genius. He was a polymath interested in all aspects of Mexico, its history, culture, botany, zoology, and geology. He helped found the Mexican Society of Natural History and used his skills as an accurate and precise painter to illustrate his studies. His main geological interest seems to have been the Central Valley. The National Gallery exhibition was divided into each of his separate areas of interest, but the main picture was in the geology section and was the Valley of Mexico from the hill of Santa Isabel, which is a view looking southeast across the Central Valley from a viewpoint at the western end of the Sierra de Guadalupe hills that form the northern edge. It's not really a landscape painting like John Constable did. This should be seen as one of many studies that Velasco did to help him understand the Central Valley. When we were looking at the painting, my wife said that it would make a good subject for a geological talk. I was not convinced that geologists would want to hear all about a 19th century oil painting by an obscure Mexican painter, but I did a bit of research and found that a lot of work had been done on the area quite recently, both by geologists and civil engineers who had dug deep wells through the valley floor. So a talk was not such a bad idea after all. The first thing I looked for was a more up-to-date picture of the valley, but most modern views just show the Mexico City conurbation. This picture is looking north across the valley with the hills where Velasco did his painting in the background. Today, Mexico City is a top 10 urban agglomeration with a population of about 25 million people, and it is difficult to work out the features of the original landscape. So I decided to stick with Velasco's painting as the best view of the valley before the spread of Mexico City. The next thing I did was to identify what seemed to me to be the main lumps and bumps. These were two snow-covered peaks, a range of hills on the south side of the valley, a big lake, an odd-looking mound in the middle of the valley, a big lump on the right, the valley floor and the foothills of the northern hills, the Sierra de Guadalupe. The valley itself is both huge and high. The area is 9,600 square kilometers, 3,700 square miles bigger than the English counties of Buckinghamshire, Oxfordshire, Berkshire, Bedfordshire and Hertfordshire combined. And it is 2,240 meters, 7,350 feet above sea level, which makes Mexico City the 8th highest capital city in the world. How on earth did such a vast, flat valley get created so high up? I gave myself 3 questions to answer. In reverse order they were: how was the Central Valley formed so high up in the mountains? Where did the mountains come from in the first place? When and how did Mexico itself arise to provide a platform for the mountains? I wondered how old Mexico might be, so I started by looking at Pangaea, the supercontinent that came together 250 million years ago. The far western edge is marked as Mexico, which means that the land is over 250 million years old. Or is it? When Pangaea split apart, in the west there was a north-south divide. The north went to Laurasia and the south to Gondwana. But where did the central bit go? It is difficult to be precise, but it seems that most, including central Mexico, just disappeared under the sea. As sea levels rose and fell over time, there would have been occasional low-lying islands, but the oldest rocks described in the Mexico Central Valley are Cretaceous limestones, which we know were laid down underwater. I did wonder why there was no mention of the famous Chicxulub meteor, but of course it collided with Earth before the Mexican mainland had emerged from beneath the waves. So when and how did central Mexico re-emerge? It started about 50 million years ago, and we have the process of subduction to thank for that. This theoretical diagram explains that subduction is the sideways and downward movement of the edge of a plate of the Earth's crust into the mantle beneath another plate. There are four key elements here. First, we have a plate under the sea moving towards and under the land plate. Second, there is the land plate being forced up by the subduction of the oceanic plate beneath it. Then there is an offshore trench where subduction starts. On this diagram, it's shown as a thick line with arrowheads pointing to the actual direction of subduction. Finally, there is an arc of volcanic mountains inland of the actual point of subduction. This is caused by water being released by the subducted plate. So how does this theory translate into reality? This map shows the tectonic plates of Central America. The thin arrows indicate the direction of plate movement, and the numbers show the amount of movement in millimeters per year. The oceanic Cocos and Rivera plates are moving towards and being subducted beneath the North American continental plate, which is uplifted. The arrow shows this movement is towards the north-northeast at the rate of 67 millimeters per year. This subduction zone has formed the Middle America Trench and the arc of volcanic mountains known as the Trans-Mexico Volcanic Belt. By the way, devastating earthquakes in Mexico City in 1985 and Chiapas in 2017 show that this subduction is ongoing. This topographic image from Google Earth clearly shows the Middle America Trench along the southern Central American coastline, as well as the mountains of the Trans-Mexico Volcanic Belt. So now we have the answers to the first two questions. 1. Central Mexico started to re-emerge from under the sea due to subduction starting about 50 million years ago. 2. The mountain range where the Central Valley sits is the volcanic arc, which is a byproduct of that subduction. So where did the Central Valley itself come from? This first map shows that the Central Valley is located in the southeastern part of the Trans-Mexican Volcanic Belt. The second map zooms in to show the Central Valley in more detail. The area within the dashed line is, roughly, the area covered by Velasco's painting. The two volcanic peaks of Popocatépetl and Iztaccíhuatl in the lower right-hand corner are the two snowy peaks in the distance in the painting. Notice that this map does not call it a valley. Instead, it is a basin because it is surrounded by mountain ranges. Remember also the altitude of the valley, 7,500 feet above sea level. The number of fault lines is also notable. This next map shows the sequence of mountain building that shaped the basin. First, in the north, was the oldest range, the Sierra de Guadalupe. This emerged about 14 million years ago in the Miocene period. This was actually the southern edge of the much larger and older Tepoztlan Formation. Then there was a period of 10 million years when nothing much happened, before the next three ranges appeared in quick succession. The Sierra de las Cruces appeared in the west, starting 3.7 million years ago in the Pleistocene period. Next, in the east, came the Sierra Nevada, starting 1.4 million years ago in the Holocene period. Finally, still in the Holocene, came the Sierra de Chichen Agustin in the south, starting from 1.2 million years ago. The two peaks of Popocatépetl and Iztaccíhuatl represent the most recent activity. They are regarded as the ongoing southward expansion of the Sierra Nevada. Now we have a lot of mountains, but we still don't have the vast flat expanse of the Central Valley, or basin as we should now call it. The next diagram tries to show how the basin came about. It should not be taken as a literal explanation of what happened, but rather as a general description of the processes involved. We start with an imaginary range of mountains that represents the Trans-Mexican volcanic belt, and then we see how material from subsequent volcanic eruptions starts to fill the space between the four mountain ranges that we saw just now. We might start with some lava flows. Next might be pyroclastic flows, which feature material that flows into gaps between the lava, and we must not forget volcanic ash, which can smother just about anything. Of course, this was not all completely sequential. Different eruptions might occur at the same time, but expel different material. And the whole process continued for thousands of years. And indeed, it is continuing to this day. The last big ash fall was in February 2024. And then we had the Ice Age. Mexico in the Ice Age. Surely not. This map shows what we all know. Ice sheets expanded south from the North Pole and north from the South Pole. But what are the dots on the map? They represent large, individual, unconnected mountain glaciers. We know these occurred in Mexico because individual terminal moraines, which mark just how far glaciers reached, are found up in the mountains of the Trans-Mexican volcanic belt, not spread out across lowlands, as is typical when you get ice sheets. Resuming our diagram showing how the central basin was formed, we can see that as temperatures rose, glaciers melted and water flooded the basin. Because this was a basin with no natural outflow like a valley would have, the water stayed but gradually evaporated, leaving silt and other sediments behind. These are called lacustrine deposits and are up to 300 meters thick in places. Finally, for completeness, I have added some fault lines and deep wells as illustrations. And that gives us the answer to the third question. How did we get such a vast, flat valley so high up in the mountains? To bring the threads together, I've come up with two different ways of summarizing the story. The first summary shows the geological eras and periods associated with Mexico's formation. Broadly, Mexico started to emerge in the Mesozoic era, with the Central Valley developing in the late Cenozoic. The first range of hills, the Sierra de Guadalupe in the north, were part of the Tepoztlan Formation and appeared in the Miocene period. The Sierra de la Cruz appeared in the west in the Pliocene. Then, the Sierra Nevada in the east and the Sierra de la Chichinosteen in the south arrived in the Holocene and recent times. Notice that the lacustrine deposits are also shown appearing at this time. This suggests that the moment the Sierra de la Chichinosteen closed off the basin, the valley or basin began to fill with volcanic deposits and water started draining from the hills. A second way of summarizing matters would be to go back to the landscape depicted in Velasco's painting and chronologically go through the lumps and bumps we noted at the beginning of this talk, from the oldest to the youngest. The oldest part is the Sierra de Guadalupe, whose foothills we can just glimpse at the bottom of the picture. Next we have two lumps that result from volcanic activity in the Sierra de Guadalupe. The odd lump in the center has been called a pyroclastic cluster, but this term is a bit controversial, as you can see from this description.
A pyroclastic cluster is not a standard scientific term, but it likely describes a discrete, coherent clump or concentration of hot, fast-moving volcanic debris. Unlike a diffuse pyroclastic flow, a cluster implies a more compact and dense collection of volcanic material, perhaps consisting of larger blocks and less gas, within or alongside a larger flow or surge.
I hope that helps. Along with the pyroclastic cluster, we have the remains of a large viscous lava flow. The Sierra de las Cruces and the Sierra Nevada are too far to the west and east respectively to appear in the picture, so the next feature is the Sierra de Chichinosteen at the southern edge of the valley. As we have seen, once the Sierra de Chichinosteen closed the valley off, the basin started to be infilled. Lake Texcoco is basically all that remains of the big lake from the end of the glacial period. Finally, we have the volcanic peaks of Popocatépetl and Iztaccíhuatl, which, as we have seen, are at the southern end of the Sierra Nevada. That is the end of the geology as such, but I have a small postscript which I find interesting. Why was Mexico City built in the Central Valley in the first place? Because the Spaniards wanted to build it directly on top of Tenochtitlan, the indigenous capital. Why was Tenochtitlan built here? Because the gods told the first king to build it where he found a harpy eagle sitting in a nopal cactus by a lake with a snake in its mouth. Velasco referenced this by adding a nopal cactus and a harpy eagle searching for a snake into his painting. Of course, he already had the lake in the picture. This story is so important to the Mexican people that it is built into the national flag, including the post-glacial lake.
You have been watching the geology and landscape of the Central Valley. Basin of Mexico. I hope you enjoyed it, and thank you for watching. This video was produced by the High Wycombe and District U3A Geology Group. The script was by Keith Spencer. Video production by Phil Platt. The narration was by voice simulation from Play HT and Hume AI.